a number of different options for storing CO2 in the underground. The sort of the first and most obvious one are oil and gas reservoirs. Why are those obvious? Well, two things. One is that we know that they have seals on top of them that enable trapping buoyant fluids, so natural gas or oil, which are kind of similar to trying to trap carbon dioxide. So we know that there's a good seal there. And second is we've extracted quite a lot of fluids, quite a lot of oil, quite a lot of water or gas. And so sort of simplistically, one thing can think, well, we could just replace that same volume with carbon dioxide. So that's sort of the first and most obvious one. So oil and gas reservoirs actually occur in what are called sedimentary basins. So sedimentary basins are rock formations that basically are made up of eroding materials from mountains. So the best example would be to think of the Great Central Valley of California. You know, it's very flat, it's just sediments all the way down for maybe 18,000 feet. So really like a bathtub filled with sediments. So those are the kind of areas you're looking for. So that's where oil and gas reservoirs occur. But within those sedimentary basins, there are other options. CO2 can be put into what are called saline formations or saline aquifers. These are basically the same type of formations as oil and gas, but instead of having oil or gas in them, they're just filled with salty water. So CO2 can be pumped into those formations if they have a good seal for storage as well. There's also been quite a lot of discussion of putting CO2 into coal beds or actually any kind of organic rich rock like organic rich shale. The trapping mechanism is different, is that the CO2 actually chemically attaches itself to the surface of the rocks where you have organic matter, and it basically permanently traps the CO2 because it's chemically attached as opposed to physically trapped beneath a seal. So those are the ones everyone talks about all the time. Biggest potential is in saline aquifers. Oil and gas reservoirs have a lot of potential and make sense because we know a lot about them. There's one more I'd like to bring up. There's been a discussion of putting carbon dioxide into basalt formations. The reason this is important is there are vast parts of the world where there aren't sedimentary formations, so India is probably the best example. And if CO2 could be put into the basalts, there are studies that show that it will react chemically and form permanently sequestered carbonate minerals, magnesium carbonate, calcium carbonate, iron carbonates, and so forth. So that's a very interesting area, but much less well studied, and it would take a long time before we were really prepared to do that on any kind of large scale. So one of the questions is, if you have a storage project that works great for the first 50 years, and then maybe even you monitor it for another 50 years and everything's fine, the question is well, what's the probability that sometime 100 years from now, 1,000 years from now, it starts to leak? In my opinion, the probability of that kind of scenario is extremely low. One of the things is, I mentioned earlier, that when you stop injecting, the pressure goes down, so that the driving force for CO2 to escape from the storage reservoir goes down very, very quickly as that pressure subsides. The second thing is that the CO2 is continuously and progressively dissolving in the water. Once the CO2 dissolves in the water, it's actually negatively buoyant now and actually can set up these convection cells that will gradually dissolve more and more of the CO2. Another mechanism, something called capillary trapping, that when you stop injecting, you've got this big CO2 plume and you've got all this water around it. Well, the water wants to what's called imbibe back into it, basically sort of be sucked back into it by capillary action. And in the process of doing that, the water actually bypasses some of the CO2. And what it does is it makes the CO2 so it's no longer all connected. So CO2 can move when it's all as a connected phase. Once you have these isolated blobs, or technically called ganglia, they can no longer move because they're not connected. So that's a very important secondary trapping mechanism. And then finally, over very long time periods, well, depending upon the place, CO2 will actually interact with the rocks and fluids to form carbonate minerals or potentially other minerals. So all of these secondary trapping mechanisms, in addition to sort of having a good site in the first place, make it unlikely that there will be a very great risk associated with long-term leakage of CO2 out of the storage reservoirs. So when you put CO2 under the ground, in an oil or gas reservoir, you might be simultaneously taking out fluid, or at least you've already sort of depleted fluid. So you're basically, it's sort of a substitution process. So sort of the issues about pressure perturbations and all are relatively slow. But in the case where you're putting CO2 into a saline aquifer, basically it needs to push, the water out of the way. And the question is, well, what happens to that water? Does it, well, what happens actually is the water does two things. One is the pressure goes up, and when the pressure goes up, the density of the water increases a tiny bit. The other thing is that the pore spaces in the rock open up a tiny bit. And whereas those are very small numbers, they do this over an absolutely enormous area. So some process which sort of takes place at the 10 to the minus 9 level, acted on over a really, really large volume, you can actually accommodate a lot of fluid. The other thing that can happen is most of these systems are not closed, fully closed. So some fraction of the water can actually migrate up through the seal, or it could migrate laterally to other areas. And so the question was, well, wow, does that sound scary? Well, typically the volume of fluid that would be put into one of these systems is something on the order of, say, 1 to 4% of the volume of the storage reservoir itself. But that's only a tiny fraction of the overall water. So you're talking about sort of introducing a new substance at the level of maybe 10 to the minus 6, one in a million. So the idea that you can accommodate the sort of 1 in a million increase in volume is not very difficult to imagine for very large basins. Oh, so the other part of your question is, does the land surface actually lift up? And it does actually lift up. And one of the most fascinating things in terms of monitoring data that's been learned is that from the Insala project, this is a CO2 storage project in Algeria, and 1 million tons per year is put into a very deep gas reservoir that also is a saline aquifer. And from satellite imagery, a scientist from Lawrence Berkeley Lab actually went independently and got the satellite data and basically was able to image the land surface inflating during injection, and actually when injection stops, it deflates. Okay, so yes, that happens, but the question really is how much? Well, it turns out it's on the order of centimeters over the entire time scale of the project. So yes, there is deformation, but at least under that circumstance, it's really very small. And that's an area where one might expect fairly large deformation, given that the pressure buildup in the storage reservoir was quite high.